Hello everyone, myself Sonia Rani. I welcome you all on this fourth live session of the course Solar Photovoltaics Fundamentals, Technology and Applications. Similar to last week, today also we'll solve some numerical problems based on the topic covered in the video lecture series of 4. Let's start without any delay. Okay, so here is your first question. So it is saying that the two photodiodes, each with an effective area of 10 cm square, are exposed to biochromatic radiations having power density of 500 watt per meter square. In a narrow bands, one around the 430 terahertz and the other around 600 terahertz. So one diode has a band gap of 1 electron volt and the other is having a band gap of 2 electron volt. So when the diode is under the reverse bias condition, so at that time the saturation current is 10 nanoampere and the diodes are operating at 300 Kelvin. So it is asking you what are the short circuit photocurrents for both the diodes. So let's first write what is given actually in the question. So let's say this is my photodiode 1, and here we will write the values for the photodiode 2. Okay, so the first thing that they have given, each with an effective area of 10 centimeter per square, 10 centimeter square. So effective area for this photodiode 1 is 10 centimeter square, and similarly for this photodiode 2 it is 10 centimeter square. The next thing is they are both having a radiation having power density of 500 watt per meter square. So the power density for the first photodiode is 500 watt per meter square, and similarly for the second photodiode it is 500 watt per meter square. Then the first is operating around frequency of 430 terahertz and the second one is around 600 terahertz. Then they have given that the band gap of the first photodiode is 1 electron volt and the other is having a band gap of 2 electron volt. So let's say we are representing it by WG1, which is your band gap of the first photodiode. It is your 1 electron volt, and for the second photodiode it is 2 electron volt. Then they have also given that the under the reverse bias condition, the saturation current, that is your I naught, is 10 nanoampere and the operating temperature is 300 Kelvin. Okay. So these are the things which are given in the questions. So we can write the photon flux. Photon flux, that is your denoted by phi. Okay, let's say this photon flux is denoted by phi. So we know the relation between the power density and the photon flux, that is given by photodensity. This is power density is equals to phi hf, where phi is your photon flux, h is the Planck's constant, and your f is representing here the frequency term. So for the first photodiode, the frequency value is 430 terahertz. Okay, so from here we can derive a expression for the photon flux, that will be power density divided by h, that is your Planck's constant, and frequency f. Okay, so for the first photodiode, that is when the frequency is 430 terahertz. Let's say call it as phi1. So the power density they have given you 500 watt per meter square. 500. Value of Planck's constant is 6.6 into multiplied by 10 raised to the power minus 34, and the frequency here it is 430 terahertz. 430, and when we will convert it into hertz, that will be your multiply it by 10 raised to the power 12. So when we will solve it, we can write it like 500 divided by 6.6 into 430 and then multiplied by 10 raised to the power 22. So when you will solve this, you will get phi1 will be equal to 0.176 into 10 raised to the power 22, or we can also write it like 1.76 into 10 raised to the power 21 photons per meter square. So is this clear to everyone? You can write yes in the chat box if it is clear. Okay. So similarly for the second frequency, we can calculate like at 600 terahertz. The same expression, using the same expression, phi2 will be equals to 500 divided by 6.6 into 10 raised to the power minus 34 and then multiply it by 600 into 10 raised to the power 12. So similarly, when you will solve this, you will get 0.126 into 10 raised to the power 22, and that will give you 1.26 into 10 raised to the power 21 photons per meter square. So this is the photon flux for the first photodiode, and this is the photon flux for the second photodiode. So is this clear to everyone? You can write yes in the chat box. Okay. So till now we have found that phi1 is your 1.76 into 10 raised to the power 21 photons per meter square. So mega, is it visible or not now? Okay. So phi2 is your 1.26 into 10 raised to the power 21 photons per meter square. Okay, then let's assume a case, means when the efficiency or the quantum efficiency is 1, so we can say the number of incident photon, means the photon that will incident will be converted into a electron hole pair. So we can write it like this. Also, if you will see, we know the relation between the energy and the frequency is equals to h nu. So we can calculate from here. For the first photodiode, it is 6.6 into 10 raised to the power minus 34 multiplied by the frequency, that is your 430 terahertz. That will give you 430 into 10 raised to the power 12. So we can write like 6.6 into 430 into 10 raised to the power minus 22, correct? And from here, so what this will give me? Anyone can tell what this value will give me? Even. I am writing here for the E2 similarly 6.6 into 10 raised to the power minus 34 multiplied by 600 into 10 raised to the power 12. So no one is replying there. What will this even will be from here? You just have to multiply these two numbers. Okay. So see, it will give you 10 raised to the power minus, if I am saying in this. Okay. And here if you will see that one diode is having a band gap of 1 electron volt. So I can write it from here. The energy band gap, which is your WG1, is 1 electron volt. So when we will convert it into joule, so we can write it is 1.6 into 10 raised to the power minus 19 joule. Okay. And your band gap of the second photodiode is 2 electron volt. That is 2 multiplied by 1.6. Please unmute yourself. If you have any doubt, you can write in the chat box, please. Okay. So that will be my 2 multiplied by 1.6 into 10 raised to the power minus 19. So that will give me 3.2 into 10 raised to the power minus 19 joule. That is the band gap of the second photodiode. So is it clear to everyone? So now if you will see, so the photodiode 1 will absorb the photons of both frequency and the photodiode 2 will absorb the photon with higher frequency only. Okay. So we can write from here the value of the current. Let's say we are the short circuit photocurrent, short circuit photocurrent, we are representing it by IV. Okay, so it is your Q times A and then phi t. The phi t is your total flux, So separately, if we will calculate the total flux for this photodiode 1, so it will be, since it will be absorbing the photons of both frequencies, so we can write it like 1.76 plus 1.26 and then multiplied by 10 to the power 21. So it will give you 3.02 into 10 to the power 21 photons per meter square. So this will be your flux for the first photodiode. And similarly, for the case of the second photodiode, the photon flux will be 1.26 into 10 to the power 21 photons per meter square. So now we will put the values in this expression. So for the first diode, the current value will be 1.6 into 10 to the power minus 19. The effective area or the active area is 10 centimeter per square. So 10 centimeter square it is, and when we'll convert it into the meter, so it will give me 10 to the power minus 3 meter square. Okay, so that means multiplied by 10 to the power minus 3, and then photon flux for the first diode is 3.02 into 10 to the power 21. So when you will calculate, so it will give you 0.482 ampere. So that is the short circuit photocurrent for the first photodiode. And similarly, for the second photodiode, we'll multiply the charge value with the effective area, that is 10 to the power minus 3 meter square, and then the total flux, that is 1.26 into 10 to the power 21. So it will give you 0.202 ampere IV2. So which is for the diode 1, that is 0.482 ampere, and for diode 2 it is your 0.202 ampere. So option 1 will be the correct answer for this question. So is it clear to everyone? Okay. So now let's move on to the second question. So the question is same, means the two photodiodes, they are given each with an effective area of 10 centimeter square, and the power density is still 500 watt per meter square, and the two frequencies values is 430 terahertz and the 600 terahertz. One is again having a band gap of 1 electron volt and the second is having a band gap of 2 electron volt, and the value of the saturation current is given, that is your 10 nanoampere. The operating temperature is still 300 Kelvin. So it is asking that what will be the open circuit voltage of the each diode. Okay, so for solving this question or numerical, you must know the relation for the open circuit voltage. So what was the value of the short circuit current for the first diode, which we have just calculated, that is for 0.482 ampere, and the second was 0.202 ampere. Okay, so we'll be using it for the further solving of the numericals. So let's write this. So the expression is VOC is equals to KT by Q ln of IV divided by I naught. Okay, where in this expression K is your Boltzmann constant, T is the operating temperature, Q is the charge, IV is your short circuit current, short circuit photocurrent, and I naught is the saturation current. Okay, so for the first photodiode 1, we can call it as VOC1. That will be and the value of this KT by Q is 0.026 volt, and it is a constant value, so we can write it like 0.026. Then ln of, for the first photodiode, the value of the short circuit photocurrent was 0.482 ampere. So let's write 0.482 ampere, and the saturation current value is 10 nanoampere. So I naught is given, that is 10 nanoampere. So we can write it like 10 multiplied by 10 raised to the power minus 9 ampere. So it will give us 10 raised to the power minus 8 ampere I naught. So that will be 10 raised to the power minus 8 ampere. So it will give you 0.026 ln of 0.48, again means divided by 10 raised to the power minus 8. So when you will solve this, so you will get the value of the VOC, that will be 0.460 volt. So that is your VOC1, that is the open circuit voltage for the first photodiode. So is it clear to everyone? You can write yes in the chat box. Okay. So we know that the short circuit photocurrent for the second photodiode was 0.202 ampere. Okay. So now we'll calculate the open circuit voltage for the second photodiode, that is your VOC2. So that will be again KT divided by Q ln of IV2 divided by I naught. I naught was 10 nanoampere, so that will be 10 raised to the power minus 8 ampere. Value of this constant, since this is all the constant value and this is equals to 0.026 volt, and then multiplied with the ln value of 0.202 divided by 10 raised to the power minus 8, that is your VOC2. And when you will solve this, so it will give you the 0.437 volt. So the photodiode 1 was having a open circuit voltage of 0.460 volt, and for the second photodiode it is 0.437 volt. So out of these, your option number 3 is the correct answer for this question. Is it clear? Okay. So now let's move on to the next question. Okay. So again, the given values are same. Effective area is still 10 centimeter square. Power densities of the radiation was 500 watt per meter square, and the frequency one values was 430 terahertz, and the second operating frequency was around 600 terahertz. The band gap of the first photodiode was 1 electron volt, and the second is 2 electron volt. I naught is again your 10 nanoampere, and they are asking that what is the maximum theoretical efficiency of each diode. Okay, so for calculating this, see, the efficiency, that is generally it is represented by eta. Efficiency is given by the P maximum output divided by input power. Correct? So if you will see here, what is the input power for both the diodes? So let's say call it as a P input, Pi. So power is what? Intensity, or the power density multiplied by area, and the unit is your in watt. Okay, so that will be, since we are talking about both the diodes and it is given the power densities is 500 watt per meter square, so the input power will be 500 plus 500 multiplied by the area into W, or that will give me 1000 multiplied by A watt. Now if we talk about the P max output we are saying, okay, so we are saying it like A multiplied by the total flux multiplied with the band gap value watt. So where this phi t is representing the total photon flux, total photon flux per unit area, we can say. This is representing here the band gap of the particular photodiode. Okay, and A is representing here the area. So from here we can calculate like efficiency, that is your P max output will divided into P input, that will give me A multiplied by phi t Wg, W divided by what, intensity, that is my 1000, this value, and multiplied by A watt. So this will be cancelled out. So from here the efficiency we can write like phi t Wg divided by 1000. So this is the expression for the for calculating the maximum theoretical efficiency of each diode. Is it clear to everyone? You can write yes in the chat box. Okay. So let's see, the expression is for the efficiency is phi t, that is total photon flux, multiplied by the band gap value, then divided by 1000. For the photodiode 1, we have already calculated that the phi t is your 1.76 plus 1.26 into 10 raised to the power 21. Yes or no? We have already calculated this value, so that will give me 3.02 into 10 raised to the power 21 photons per meter square. Okay, so that is for the photodiode 1. So let's call it as phi t1. And the photodiode 2, we are calling it like phi t2, and that is your 1.26 into 10 raised to the power 21 photons per meter square. Okay, so we have this value, and we are also having the band gap value of each photodiode. For the first one it is your 1 electron volt, and for the second one it is 2 electron volt. So let's calculate the efficiency 1 for the for photodiode 1. So that will be my okay, so that will be your 3.02 multiplied by 10 raised to the power 21 times of what is the band gap value of the first photodiode, that is your 1 electron volt. So when I will convert it into joule, so it will be my 1 into 1.6 into 10 raised to the power minus 19 joule. So simply I can write 1.6 into 10 raised to the power minus 19 joule. And for the second photodiode, it will be 2 multiplied times 1.6 into 10 raised to the power minus 19. That will give 3.2 into 10 raised to the power minus 19 joule. Okay, so for the first photodiode, it is 1.6 into 10 raised to the power minus 19, and then dividing it by 1000. So on calculating, it will give you 3.02 into 1.6, 10 raised to the power 2 into 10 raised to the power minus 3. We can write it like, and since we are calculating the efficiency, so all these are given in percentage, so we'll multiply the expression by 100 here. So for the first photodiode, the maximum theoretical efficiency value will come 48.2%. Okay, similarly, if you will see for the second photodiode, let's say call it as eta 2, and that is my 1.26 into 10 raised to the power 21 multiplied by the band gap, that is 3.2 into 10 raised to the power minus 19, and then dividing it by 1000 and also multiplying it by 100. So that will give the value of eta 2 equals to 40.3%. Okay, so 48.2 is for the first photodiode, and for the second photodiode it is 40.3. So out of these, the option number 1 is the correct answer for this question. So is it clear to everyone? You can write yes in the chat box, and if you have any doubt, then you can also mention that. Okay, what about the others? Minute is responding yes. Okay, I think it is yes. You can please unmute yourself if you have any doubt. I think someone has raised a hand. Okay, sir. Okay, so let's move on to the next question. So here if you'll see, all the information that we were using till now is same. The effective area is still 10 centimeter per square, 10 centimeter square. The power density value is again 500 watt per meter square. These frequency values are still 430 terahertz and 600 terahertz. Band gap value is again 1 electron volt and 2 electron volt. And the saturation current is again 10 nanoampere. Operating temperature is 300 Kelvin. So it is asking you that what is the maximum power that each diode can deliver to a load. Assume that there is no series resistance in the diodes. Okay, so let's solve this question. So we know the relation, actually the voltage the voltage at the maximum power output let's say it is your Vm, correct? And we know the relation that 1 plus QVm divided by KT multiplied by ln times of, sorry, this is your exponential of Vm multiplied by Q divided by KT, and then equals to IV divided by I naught, where Q is again your charge, this is your Boltzmann constant, T is the temperature or the operating temperature, this is your short circuit photodiode current, and this is the saturation current value, So in just now in one of the previous numerical we have solved that IV1, that is the short circuit photodiode current for the first photodiode, was 0.482 ampere, and for the second photodiode it was 0.202 ampere. Correct? I naught, they have given you 10 nanoampere, so we can write it like 10 raised to the power minus 8 ampere. So we know the one thing, that your KT divided by Q is your 0.026, right? So when we will rewrite this expression, so we can write it like 1 plus Vm divided by 0.026 e exponential of Vm divided by 0.026, and then equals to, for the first photodiode if I am considering, so it will be 0.482 divided by 10 raised to the power minus 8. So it will be my 0.482 into 10 raised to the power 7, sorry, 10 raised to the power 8, or we can write it like 4.82 into 10 raised to the power 7 here. Similarly, we can also write for the second photodiode. That will also give us, let me change the color to differentiate. So for the second photodiode, it is your 1 plus Vm divided by 0.026 exponential of Vm divided by 0.026 is equal to 0.202 divided by 10 raised to the power minus 8, and that will give me 2.02 into 10 raised to the power 7. So is it clear to this point? So when you solve the expression for this photodiode 1 and photodiode 2 for the maximum power output, so Vm1 will be your 0.388 volt and Vm2 will be your 0.367 volt. Okay, you can solve this equation number 1 and equation number 2. Okay, so we have our Vm1 for the first photodiode, it is 0.388 volt, and for the second photodiode it is 0.367 volt. We are also having the short circuit photocurrent for the first diode, that is your 0.482 ampere, and for the second photodiode it is 0.202 ampere. Okay, so the question was that what is the maximum power that each diode can deliver to a load, assume that there is no resistance in the diodes. Okay, so for the maximum power through each diode, that will be your Pmax, let's say we are calling. So power is what? Voltage multiplied by the current value. We have already obtained the value of Vm, that is your maximum power, maximum voltage point for both the diode, that is your Vm1 and Vm2, but still we are not having the value of Im. Okay, so first we will calculate the value of Im, and then we will put the value of the Vm and the Im in this expression only, say like call it as equation number 1. So for the maximum current, that is your Im, that can be given as IV minus I naught bracket e raised to the power q v divided by kt minus 1. So let's calculate for the first photodiode. We are calling it like IM1. So that is all. That will also be my IV1 value, and that is your 0.482 ampere. 0.482 ampere. I naught is 10 nanoampere. 10 nanoampere when we convert into the ampere, so it will give me 10 raised to the power minus 8 ampere. That is 10 raised to the power minus 8 e raised to the power. Vm value for the first photodiode is 0.388 and divided by the value of these are all the constant kT divided by Q for a particular operating at the room temperature, that is around 300 Kelvin. So it will be your 0.2026 volt. So it will be 0.026 and then minus of 1. So this will give you the maximum current through the first photodiode. Okay, so that will be your 0.452 ampere. This is for the first photodiode. Similarly, we can also calculate the maximum current through the photodiode 2. So that will be my IM2. The value of IV for the second photodiode is 0.202 ampere. So that is 0.202. Then again, I0 is same for both the photodiodes. So that will be 10 raised to the power minus 8 multiplied by e raised to the power 0.367, that is the maximum voltage through this photodiode 2, and divided by the value of 0.026 and then minus 1. So this will give me the value of the maximum current through this photodiode 2, and that is your 0.189 ampere. Okay, see, now we are having the maximum voltage through across both the photodiode and also the corresponding maximum current through these photodiodes. Now what was the question? The maximum power. So the maximum power P max through the first photodiode is P max 1 is equals to Vm1 multiplied by Im1. So what was the value of Vm1? That is your 0.388 volt multiplied by 0.452 ampere. Okay, so it will give you 0.175 watt. 0.175 watt. Okay, so that is P max 1. Now for the second photodiode, the maximum power will be equals to Vm2 multiplied by Im2. The value of Vm2 is 0.367 volt and multiplied it by your 0.189 ampere. So it will give you 0.069 watt. So that is the maximum power through this second photodiode. So out of this option, if you will see, the option number second is the correct answer for this question. So is it clear? Okay. So now let's move on to the next question. So the question is, the value of the zenith angle for the AM 1.5 is. So first of all, what is this AM 1.5? This is actually stand for air mass 1.5. So suppose that this is your sun and this is the Earth's ground, and here is the Earth's atmosphere, and the radiations are coming from the sun like this. So outside the atmosphere there is no air mass. Here air mass is 0. Okay, and when I'm talking about the radiation which are incidenting just perpendicularly on the surface of the Earth, that is, it is passing through the atmosphere once. Okay, so when the position of the sun will change, so let's say now sun is at this position, so the path length that will be traveled or covered by the radiation to reach the Earth's surface, that will also change. So corresponding to this value, the intensity of the solar radiation is different. Okay, so we know this relation air mass x, we can say, is equal to 1 divided by cos time of theta, where theta is this angle. Okay, so if we will calculate from here, the value of the third option is your cos 0. What is the value of cos 0? That is your 1. So that will give me air mass x is equals to 1, or we can call it like air mass 1. So for air mass 1, the zenith angle must be your 0 degree. But here we want to calculate the zenith angle for the air mass 1.5. So when we will take theta equals to 48.2. Okay, so that will give me cos times of 48.2. So is someone is having any doubt in the previous question? You can write in the chat box. Okay, so that will give me 0.66. So for calculating the air mass x, we are saying it 1 divided by 0.66, and that will give me 1.5. So that will be for the air mass 1.5, the zenith angle must be your 48.2 degrees. Is it clear to everyone? Please write yes in the chat box, and if you have any doubt, then you can also unmute yourself. Okay, so now let's move on to the next question. So the next question is, calculate the number of the photons that will be absorbed in the solar cell if the current density obtained is 46 milliampere per centimeter square. So the relation between the current density and the photons, number of photons, that is basically asking you the photon flux, actually photon flux. So current density and the photon flux is represented by J equals to Q times of phi t, where phi t is your total flux for photons per meter square or per unit area, whatever it is. So here we want to calculate the flux, the value of the power, the current density. So J is actually representing the current density divided by the charge. So the value of current density is 46 milliampere per centimeter square. So we'll convert it into the ampere, into 10 to the power minus 3 ampere, and when we will divide it 1.6 into 10 to the power minus 19, and also you can see that it is given in U per centimeter square. So when we'll convert it into the meter square, so that we can multiply it with this value. So it will be mine okay. So the thing is, if it is given that you are talking about the photon flux in meter square, only you will do this thing in that case. But since it is not mentioned here, you can see that it is not mentioned that here that you need to change actually the unit, so we'll not include this value. So when we'll divide this, so 46 divided by 1.6 into 10 raised to the power, that will give me minus 3 into 10 to the power 19, or the photon flux, that will be 2.875 into 10 raised to the power 17. So after calculating, you can get this answer, which is your option number 1. So option number 1 is the correct answer for this question. So is it clear? You can write yes in the chat box. Okay. So now the next question is, so what among these options, so what is the desirable property of sensitizer? So if I'm using this dye sensitizer as my active layer in a solar cell, so among these, what should be the desirable property? So the first option is the low absorption coefficient. So what is the absorption coefficient actually means first? So absorption coefficient tells you the amount of light absorbed by a particular material per unit length. Okay, so suppose that I consider two materials. One is my this material, say like M1, and another is my this material M2. Okay, so it is my M2, and I'm saying that the material 1 thickness is greater than the thickness of material 2, which is also visible from these two boxes you can see. And also it is given that the material 1 is having low absorption coefficient, but M2 is having high absorption coefficient. So for a particular sensitizer, if I am saying, so we can consider that for a good sensitizer, it should be the property that in a very thin amount of material, it can absorb a large amount of light. Okay, so obviously the low absorption coefficient is not a desirable property for a sensitizer. So this option number 1 is eliminated from here. The second option is, does it have the low photostability also? So when I'm talking about the photostability means how much it is stable, when it is illuminated, under the solar radiation. Now again, for a good property of a sensitizer, it must have a high photostability. So since at the last we will be using it in a solar cell, right? So it should have a high photostability, otherwise the case will be the degradation of the device will start soon. So option number 2 is also gets eliminated. So option number 3, which is your wide range of spectrum, is the correct answer for this question. So is it clear to everyone? You can write yes in the chat box. Okay. So the last question is, in the 0D quantum dot, the motion of the electron is restricted from. So can you guess, students? So what will be the correct answer for this question? Here we are talking about the 0D quantum dot. Any idea? Okay, so Kritika is saying option number D. Manoprada is also saying the option number D, all direction. That means Tripti is also saying all directions. Okay. Dr. A. Guru Sampat Kumar is also saying D. Juliet is saying option C. Okay. Minal is also saying all direction. Annapurani is also saying all direction. Okay. Great. I think most of you have already got up to the correct answer. So if you will see here, So this is the case, means for the 3-dimension quantum dot we are saying, or it is called as a bulk. So electrons are actually free to move in all the directions. You can also see in this diagram. So electrons are free to move in all direction available. In the case of 2-dimension, motion of electrons is restricted from one direction. So for the 2-dimension, we can consider an example of quantum well. So its motion is restricted from one direction only. In one-dimensional case, the motion is restricted from two direction. So we can consider a quantum wire, as you can see. So the this motion of the electron is actually restricted from two direction. And when we are talking about the 0-dimension, that is quantum dot, and that is in the case when the electron is restricted from all the directions. So it's also visible in the diagram here that the motion of the electron is restricted from all the direction. So for this question, so option number D, that is your all direction, will be the correct answer. Okay. Okay, so thank you everyone. This is all for the today's class. We'll meet again in the next class. Thank you.